Day 2 of the binomial theorem. So if I wanted to expand any binomial to the power of n, this formula allows us to find any term number in that expansion. So if I wanted to expand something to the power of 6, I wouldn't actually have to expand the entire thing and look for the, in this case, the fourth term. This formula allows us just to use any term number, or to find any term number. So in this formula, n is obviously our power value, right, of our expansion. T of k plus 1 would be the term that I'm trying to find. So in this case, if I'm finding term 4, which is what that's asking me to find the fourth term, that would mean this k plus 1 value. Well, what number plus 1 would give me 4? This would tell me that k would have to be 3 in this case. My n value would be 4. And then in terms of x and y, well, this case x would represent 4b and y would represent a negative 6. So if I wanted to find my fourth term in this expansion, I can just refer to this formula. And this formula is on your formula sheets. So the fourth term would be I would take n combination k. Well, my n value is 6. Sorry, I should have wrote this as a 6. My n value is 6. Combination k, in this case, would be a 3. My x value is a 4b, so I'm going to go 4b to the power of n minus k, so 6 minus 3, and then times y to the power of k. Well, my y value is a negative 6. My k value is 3. So my fourth term, so now I'm going to start to evaluate. Oops, this n value should be 6. So I'm going to take a 6 combination 3, which gives me 20. 4b to the power of technically 3. So I'll just rewrite this. So now I'm actually going to start to take these to the powers of 3 and 3. So 4 to the power of 3 ends up to be 64b cubed. Negative 6 to the power of 3 is negative 216. And now I'm going to multiply all of my coefficients. So my fourth term in this expansion, if I were to expand it all out, the fourth term would end up being negative 276,480b cubed. And we're done. All right, moving on to example number 4. Well, example number 4, it asks us to find the middle term of the expansion. So we have to recognize that a middle term will only occur when the exponent on your binomial is even. And the reason for that is when n is 8, recognize that this means there's always one more term in the expansion. Okay, so there's actually 9 terms in the expansion, which then tells me the middle term of 9 terms is going to represent the 5th term. So here I'm looking for t of 5. So again, using this formula, I'll just rewrite it up here. I'm now going to find the 5th term of this expansion. So here my k value would equal 4. Because 4 plus 1 would give me the 5th term. My n value would be 8. And my x is represented by a 2x. And my y is represented by a negative 5. So I'm going to substitute into my formula. So I'm going to take 8 combination 4 x, which is really a 2x, to the power of n minus 4. So 8 minus 4 would give me 4. And then this would be a negative 5 to the power of 4. So my 5th term, if I evaluated this now, 8 combination 4 evaluates to 70. 2 to the power of 4 is 16. Negative 5 to the power of 4 works out to be a positive 625. So the middle term in this expansion would be 700,000 x to the power of 4. And we are done. Example 5. One term in the expansion x plus a to the power of 10 is 3,281,250 x to the power of 4. Determine the numerical value of a if a is a value bigger than 0. So a has to be positive. So again, I'm going to think about my formula. Okay, and so what I want to try and figure out is what term number we're talking about. So we do know that n in this case would be 10. The other thing we're given is that the exponent on x, which relates to this guy, is to the power of 4. So this part of my formula represents x to the power of 4. So x to the n minus k is represented by x to the 4th. Well, technically, I know my n value is 10. So then that would tell me that 10 minus 6 would equate to 4. So that tells me my k value needs to be 6. All right, so now we're actually ready to solve this. So we actually know the term value in this expansion, so that's going to represent t of, so here we're talking about the 7th term. Because k is 6, we're talking about the 7th term. So the 7th term in my expansion is 3,281,250 x to the 4th. I'm now going to make this equal to my equation. So now I can start substituting in the values because I do know our n value and I know my k value. So I'm going to go 10 combination k, which is 6, x to the power of 4, because 10 minus 6 is 4. And then our y value is represented by a to the power of k, which is 6. So what I want to do here is I want to rearrange this equation and solve for a. So my left side is going to stay as is. I'm going to evaluate 10 combination 6, which works out to be 210 x to the 4th, a to the power of 6. So now if I isolated a to the 6th, I'm going to divide both sides by this 210 x to the 4th. So then we're just left with an a to the 6th. Over here, our x to the 4th cancel out. If I divide these two values, I'm left with 15,625. And now to solve for a, I'm going to take the 6th root of 15,625. So when we do that on our calculators, we get a is equal to 5. So the numerical value of a would be 5. All right, question number 6, example 6. Find the constant term in the expansion. So the constant term is represented by the term with no variables attached to it. It's just a number, right? It's a constant. So what does that tell me? It tells me that in my expansion of simply x plus y, but in this case x is 2x and y is a negative 1 over x cubed, what has to happen when we multiply these expressions to some power, the x's need to cancel. And so if the x's cancel, then that's going to create our constant term. So what we want to think about is not necessarily about like coefficient, but recognize that when I expand something x plus y to the power, in this case 15, that the exponents on x and y always need to add to 15. So it's almost a guess and test method to figure out, well, at what point will these cancel? So if I take a 2x and I take that to the power of 10, and then I multiply, I really don't care what is happening with the coefficient. All I'm looking for is when these two values are going to cancel. And if I multiply that by a negative 1 over x squared to the power of 5, because 10 plus 5 would give me 15, well, 5 needs to apply to this exponent. So x squared to the power of 5 really ends up, so this is going to be x to the 10 over negative 1x to the 10. So this is the point where they're going to cancel. So how this helps us is this, we can now determine our k value. And our k value is technically related to, or not necessarily this exponent, but is this exponent in our expansion. Right? So in this case, this tells me that my k value needs to be 5. And my n value we know is 15. So what that tells me, because my k value is 5, the constant term is going to be represented by the 6th term of my expansion. So I'm looking for the 6th term. All right, so now I'm going to just substitute in our values. So my n value is 15, so I'm going to go 15 combination 5 times x, which is a 2x, to the power of 15 minus 5, which is 10, times negative 1 over x squared is my y value, to the power of 5. So I'm going to start to evaluate. So 15 combination 5 evaluates to 3003. 2 to the power of 10 evaluates to 1024. This is going to be x to the 10. And then negative 1 to the power of 5 is going to be a negative 1 over x to the 10, because x squared to the power of 5 would be x to the 10. So these are going to cancel, and my constant term that we're left with, if I multiply these now, 303 or 3003 times 1024 times a negative 1 works out to negative 3,075,072. So this is represented by my constant term. So to find that constant term isn't always straightforward. You have to do a little bit of guess and check work with these terms to figure out at what point are your variables actually going to cancel. Okay. All right, so, and finally the last example. Example number 7, it says, how many terms are in the expansion 2a minus 7 to the power of 8? So we know from the properties of expansions that there are always one more term. The number of terms in any expansion is going to be represented by n plus 1. So I'm simply going to take 8 plus 1 gives me 9 terms. If there are 10 terms in the expansion, then of 2a minus 7 to the power of 2m minus 1, find the value of m. Well, again, we know the number of terms is represented by n plus 1. N is represented by a 2m minus 1. So the number of terms in my expansion is 10. This should equal an n, which is 2m minus 1, plus 1. So this is n, plus 1. So my 1's cancel, so I'm just left with 10 equals 2m. So my m value works out to be 5. Okay, and that is the end of the binomial theorem.